let's start recording.
Okay.
Okay, welcome everyone to today's One World IAMP Mathematical Physics Seminar. And this is an official seminar of IAMP, International Association of Mathematical Physics. And if you're new to this seminar and if you're watching this on YouTube, please try clicking the M intersection phi logo that you see down there and go to the About section. Then you will see the link to the main page and also the instruction about our mailing list. Okay, so it is our great pleasure, I really mean it, to have Michael Aizenman today in this seminar series. And of course, Michael needs no introduction. He's one of the greatest. And today he's going to tell us about his recent work on the BKT phase transition. So Michael, please, we are looking forward to your talk.
Well, thank you. Thank you for the invitation. It's a great pleasure to be here. I see many familiar faces and friends. I started to share the screen. Does it show up? Yeah, thank you.
That's great.
Now, just to explain, I see that there are 40 participants at this point. I cannot see all those who may raise hands. So please feel welcome to interrupt with questions and comments. And I would appreciate if the moderator would alert me to one if there is somebody. Just speak up or raise your hand. The moderator would alert us to. So the title of the presentation is listed here. It's a new perspective on a pair of two-dimensional phenomena. One is the delocalization in the random height functions, plural, models of random height functions, and the other is the Bogolyubov-Kosterlitz-Thouless phase of O2 symmetric two-component spin models. All that I'm saying is a joint work with Matan Harel, Jacob Shapiro, and Ron Peled. The version which is presented here was uploaded a week ago on the archive, so further details can be found there. Indeed, there are many moving parts to the story, and I would not be able to cover it all. So please do not hesitate to ask questions, make corrections, and so forth. I will try to at least illuminate some of it. So there are two themes, as the title suggests. One is delocalization in random height functions, and the other is the BKT phase of two-component spin models. And let me jump to the first one just to outline what this is about. So a simple example of an integer-valued random height functions is what is referred to here as the ZGF. Z is a twist on GGF, which is the Gaussian free field, GFF, Gaussian free field. So ZGF is the integer-valued Gaussian field. Over a given graph G, and V denotes the set of vertices E edges, the ZGF is given by a random function, which we denote by N, defined over the vertices, for which the partition function is just sum over all configurations which are integer valued with the Dirichlet boundary condition. So the function vanishes at the boundary, and weights which look like the familiar Gaussian field, which is exponential of minus lambda over 2 times essentially the gradient of n squared. Lambda is the coupling constant. At positive value of n, the probability measure, the Gibbs measure of this random field is given just by the measure over which the sum is performed here, normalized so as to be probability, so it's divided by the partition function. Now, were you to ignore the discretization and just replace n by continuous variables, this would be a regular Gaussian field, a so-called free field. And it's good to keep this in mind. Notice that when lambda is very large in this case, the differences would be, the gradient would be rather small. And in that case, the effect Oh, sorry. No, I have to stop and think. Yeah, the typical value of the gradient under that should be of, so there's a characteristic length which is 1 over the square root of lambda. So if lambda is small, the typical differences may be expected to be much larger than the discretization size. You may think that for lambda small, what is true for the regular Gaussian field may apply to this one, and that's indeed the case. So to come with a precise definition, we say that this integer valued Gaussian field is pinned or exhibits localization if in the infinite volume limit, the limit in which you take the size of the system to infinity, the variance of n at any site x is finite. If it diverges, it's said to depin or be delocalized. Now, basic
May
results
I ask a question?
are, yes, please.
Are we aiming for the infinite volume? So, or are we just restricting our attention to the finite volume?
Yeah, so we start by looking at finite volume, and then the question of interest is what happens with this random field when the volume is taken to infinity.
Because what I know is that if we want to eventually aim for the infinite volume, then the periodic boundary condition is more preferable than the Dirichlet boundary condition. That's what I know. But I'd like to ask your opinion about this.
I see. Okay, you would notice that periodic boundary conditions are not used here because because the action in this model is invariant under uniform shift of n. So were it to sum over periodic boundary conditions, you would see that the sum even in finite volume would diverge, since changing the configuration by a uniform shift preserves the action, and with periodic boundary conditions, it also preserves the boundary conditions. So in a way, this system possesses a global shift symmetry. And the question which we are discussing to some extent is the symmetry breaking, which may be associated with that. So as with any system which has a symmetry, you study the symmetry breaking by imposing, for example, boundary conditions or some other term which does not respect the symmetry, and then ask whether in the infinite volume limit, when the boundary is taken to infinity, the Gibbs state is still affected by the symmetry breaking term. Does this answer the question?
Oh, I see. Thank you.
Thank you. So I'm glad you asked. So that really gives me a chance to explain this. It's a question of shift symmetry breaking or not. So if you think of intuitively what does this correspond to, this is kind of an elastic sheet which can fluctuate at random but is tied at the boundary. And there are two possibilities. One is that as the boundary recedes, the fluctuations build up, and deep inside the system, say the origin or any other fixed site, the variance would diverge, which, by the way, is what happens with the simple Gaussian measure. Or else, the other possibility is that it stays finite, in which case you have an infinite volume Gibbs measure with this action. But in fact, in that case, there will be infinite number of infinite volume states which differ by a uniform shift of the level at which the fluctuations occur. So that's the symmetry broken phase. So there are different terms which at the end convey the same situation. We say that this random surface is pinned if it does not fluctuate, the variance stays finite, and otherwise it's delocalized or depinned. Now, in any dimension, the basic basic results which are valid in any dimension are that for any value of this coupling constant lambda, the infinite volume limit exists, namely, as you may intuitively expect, as you send the boundary away, the fluctuation, the variance at the origin only grows. It's monotone in the volume. So for that reason, the limit L tends to infinity exists. It may be finite or not. And the other statement, now the existence, what I said so far, is very nicely captured by an argument which was presented recently by Lammers and Ott, who prove an FKG type property for the absolute value of the field. So that can be used to prove existence of the infinite volume limit in the sense which I described. And then again, not very surprising, the limit, the expected value of n squared, the variance, is monotone, decreasing in lambda. Now, such results for spin models have been obtained in various situations using the Ginebra inequalities. For random height functions, the result is new, and for that we applied a very, very beautiful inequality of Regev and Stephens-Davidowitz, which I will mention below. In any case, it permits you to conclude that the monotonicity of the variance in lambda, with your physical intuition, that's a totally expected result. But often there is a gap between what you feel in your bones is correct and what you know how to prove. So, okay, the limit exists, is monotone. From this, it follows that there's a naturally defined critical value, lambda c, at which the transition from confinement to deconfinement may occur. But this transition is a two-dimensional phenomenon. In one dimension, this model, this random field has a Markov property, and when you look at the history of this function looked from a boundary, it actually performs a random walk. And as you know, the random walk in one dimension, the position of the random walk drifts to infinity. The variance increases. So in one dimension, the integer valued Gaussian field delocalizes for all positive lambda, no matter how large. Conversely, in dimensions larger than 2, this random surface is always localized in the sense that the infinite volume exists of these states, and you get a fluctuating surface which is held in place by the boundary conditions. Somehow, as the dimension increases, the effect of the boundary, as you know, gets only increases, and 3 or more dimensions, in fact, any dimension greater than 2 suffices to localize it. So 2 dimensions is the only dimension which you see for such short-range couplings, the possibility of a transition between localized and delocalized phase. Now, so this is kind of an upshot of the transition for one of the players in this story. It's the random height function. Now, it's well known that this random field is related through a duality transformation to a 2-component O2 symmetric spin model, for which, in the case of the integer valued Gaussian field, the interaction is almost like XY, but not quite. It's the Villain interaction. So just to put it on, to put the reference on the page, let me say, actually, let me see, I guess I should go, let me switch to this, the figure is already drawn. When you talk about duality, the duality is between the random height function on a graph and the spin model on the dual graph. So just to indicate duality, here is a graph which is not self-dual. So if the I prefer to refer to the height function on the dual of G, that's G star, and in this case, that would be the graph over which the height function is defined. It's defined over vertices of this graph, and the vertices of this hexagonal graph happen to correspond to faces of the triangular graph on which the spins would be defined. The basic relation is that we start with a partition function. The partition function of ZGF at coupling lambda on the dual to graph G through transformation, which we may skip for a moment at first, is related to the partition function of the Villain model on graph G. So notice the G star here and G there. The coupling is lambda for the random height function and beta for the spin models. They are again inversely related. The partition function of the spin model is integral over spins. I'm now, for the purpose of this, we are writing the spin model as sigma at site u to be e to the I theta u. So the integral that you see here is really integral over spins, which are associated to the sites. And the Gibbs factor, except for the fact that we are summing over those shifts, the Gibbs factor is very similar to the exponential of e to the minus beta times cosine of theta u minus theta v. This is the usual, what's written here would be the usual xy model. Oh, sorry, excuse me, I think that it's a plus here, probably. Yeah, this is the dot product. Oops, sorry. This is the dot product of two neighboring spins, and you are summing over pairs of neighboring spins sigma uv. Except that in the Villain model, the one which emerges through the duality transformation, the cosine is replaced by the, this Gibbs factor is replaced by the Jacobi function, which has much of the structure of what's seen here. In fact, one of the observations which became very meaningful for me personally through this work is that actually the Villain interaction to some extent is even more appealing than the more natural from some perspective to look at than the XY model. Often it's presented the other way around. Often people start by having the natural spin-spin coupling as the starting point, and then one explains that this should not be that far from it because it has the same periodicity, same structure of optima, and so on. I will come to the point. Now, the spin-spin correlations of the Villain model are given by the expectation value of sigma x, sigma y, which is the same as the expectation value of either plus or minus e to the I difference in the angle. The duality relation by which the random field, so the integer valued Gaussian field is related to the Villain model, under that relation, you may ask, what is the expression in terms of the random field of the spin-spin correlation function? And what emerges is actually this beautiful formula. That's not new, that's well known, in which the spin-spin correlation is the ratio between the partition function of the random height function modified by the insertion of this operator. So what you read here is sum over the configurations of the random height function, which vanish at the boundary, and the weight is minus a multiple of the gradient square, except that the gradient is modified locally along a path which links the sites x and y. So let me explain that. X and y are the sites at which we are looking at the spins. Take any path gamma linking them. Sorry, x and y are here. Take a path linking them. And now, for the dual lattice, we are associating with this what's denoted here as gamma xy, which is sort of a one form, which is used to modify the action. Namely, when you look at the effect of so gamma is equal to 1 over those edges which are transversal to the path. And the effect of this is essentially to encourage the system to produce a dislocation. So it's not a hard constraint, but it modifies the measure in such a way that the optimal weight is given to a configuration which actually makes a step here. You're discounting the penalty for having a step along this path.
May I ask 2 questions?
Yeah.
So first, is it that are you dealing with only microcanonical ensemble? Like there's no chemical potential or something other than just the temperature?
I would refer to it as a canonical ensemble. It's there is no each side has a spin. The number of spins is just the number of sides.
Yes.
So, the fluctuating quantity here is the energy of the configuration, and what you have here is a Gibbs factor. So since we do not have chemical potential because all sides are occupied by spins.
Yes.
And the only the fluctuation here in terms of the spin system is in the orientation of the different spins. The weights are controlled by the Gibbs factor, where you may think of this as the closest, as a very close expression to the more standard Gibbs factor, where what you see up here is the energy minus the energy, and beta is the inverse temperature.
And in the formula for the correlation function, may I understand the formula, the exponential decay, as some kind of, like, in the language of quantum field theory, can I understand it as some kind of an analogy to mass gap or something like that?
Yes. So the exponential decay, I mean, what you see here is like also what you see in case of, say, the simple Ising model. You have spins which fluctuate, and the correlation is just measures the amount of correlation which still exists. Typically, this would either this would be stronger at short distances and then decay. If there is long-range order, the infinite volume limit of that is non-zero. In the absence of long-range order, this decays, and the correlation function expresses the rate of correlation, which is decaying with the distance, unless there is long-range order. So that's if you define the correlation on the left side within the spin model. What the formula presents is what the formula here expresses is how is the spin-spin correlation expressed, or where do you find it in terms of the dual model. So if you start from the spin system, what's written in this box is not the most natural way to think about the spin-spin correlations. The natural way is to think about this as there is some Gibbs distribution, fluctuating spins, and they decorrelate at a certain rate. Since you have in a way, there's another set of variables which are essentially correspond to sort of a Fourier transform of the measure of spins. And you may ask, what is the mathematical expression for this correlation in terms of these variables n? Did I address your question?
Oh, I was just wondering if this exponential decay implies that there is a mass gap in this model. That's
Yes.
what I was just asking.
Yeah, that's pretty much a matter of definition. Namely,
I see.
there's a transfer matrix, and if you express the spin-spin correlation through the transfer matrix, there is indeed the rate of exponential decay corresponds to the spectral gap of that
I
matrix.
see.
above zero. And then we refer to this as the mass of the system. In particle theory, when you are looking at local observables, the decay rate can actually be associated with masses of particles in this theory.
Yeah. So, but probably we can postpone this kind of analogy question at the end to the end
Well,
of the
it's
seminar.
good because otherwise I
let's
hear
go.
only myself, and it's a pleasure to hear other voices as I talk.
Okay. Okay. But anyway.
Okay. But now your question brings us to. Before I move on to the next point, here's a curious fact about this relation. You see, spin-spin correlation depends only on the sites xy, whereas in the formula which I gave here, I'm referring to a particular path linking x with y, in a way that the spin-spin correlation is, to repeat what I said, expressed as the effect of introducing a dislocation favoring deformation operator. It's similar, it may remind you of the disorder variables for Ising models. Such a structure appears there. And just as in the other example, you should notice the homology, namely, while gamma appears explicitly in this formula, the dependence on gamma is such that the value of this is not modified under the formation of the path. And you may ask, how do I see it here? Well, if instead of using this path, you would take another, like what I just plotted here, the shift, the deformation which takes this path there into this one can actually be viewed as a gauge transformation in which it is absorbed by just shift of the values of n by a unit over the region which is swept as you move the line. In any case, this is just a side comment, so I don't want to dwell on that, but you may notice it. Now, as I said, there are different two-component ferromagnetic spin models, and the one which to some extent is more natural if you come from Ising systems is the XY model, for which the partition function is integral over the spins, and the action is with the action which is sum over pairs beta times dot product of the spins, which in our language corresponds to that. The Villain model, which I presented before, replaces this by that, as I said. Now, in two dimension, you have the Mermin-Wagner theorem, which says that the symmetry of rotation of the spins, which is a continuous symmetry, is not broken, which means that the spin-spin correlation decays to zero. So it does not assert that there is a mass gap, but it asserts that the correlation has to decay to zero, with or without a mass, as mentioned before, namely exponentially or slower. And the big excitement about the Berezinskii-Kosterlitz-Thouless phase transition is that in this model, while there is no transition to long-range order, there exists a phase transition, and there is a range of temperatures from 0 to up to critical point. There's a range of temperatures over which the decay of the two-point function is actually by a power law. The power law depends on beta. Some of the history of the subject, well, there is a paper by Berezinskii, quoted here. It was also discovered by Kosterlitz and Thouless. The Villain model, I have the reference listed here. And then the early explanations of this phenomenon of existence of slow decay of correlations used two sets ideas. One is the renormalization, vertices, and symmetry break. Well, one is presented in physics terms in the paper by Jose, Kadanov, Kirkpatrick, and Nelson. it outlined many of the ideas which were found very fruitful for the study of two-dimensional models with vertices which are related to that. The rigorous derivation came in the groundbreaking paper by Froelich and Spencer, the Kosterlitz-Thouless transition in two-dimensional abelian spin systems and Coulomb gas. In the analysis which is presented here, the problem is mapped onto a system with vertices whose interaction is the logarithmic Coulomb potential in 2 dimensions, and it's the logarithmic nature of this interaction which leads to the existence of phase transition. Essentially, if you have logarithmic interaction, the energy, the competition between energy and entropy starts to be explicitly temperature dependent. So the rigorous analysis which was introduced here, let's see, I think at time, focused on the study of the deviations of the action that I described before from just simple Gaussian behavior, and you can trace it to the potential presence of Coulomb charge configurations, which capture the deviation from simple Gaussian structure. It's been quite a work. The approach introduced the multi-scale analysis and was subsequently applied to many other challenging problems, including the Anderson localization. It's rather technical, and rigorous analysis of this continues to be sharpened. Among the more recent works is beautiful work by Garban and Sepulveda, 2020, quantitative bounds on vertex fluctuations in 2D Coulomb gas. So it's a whole machinery which deals with a number of problems. So I presented, just where we are in the talk, I presented the two players in this model. To go back to the beginning, we talked about delocalization random height functions and the BKT phase transition. Both were initially established through this Coulomb charge analysis, Coulomb gas analysis of Froelich and Spencer. Recently, percolation type methods were successfully deployed in the study of the random field, so of the integer valued random functions. And here is a number of relevant papers. I think it may have been Scott Sheffield's thesis work on random surfaces, where various basic results of such random surfaces were presented. There are papers which I would not read here, but are displayed on the page. Random surfaces appear in various variants. So one of them would be surfaces which are constrained, rather than having Gaussian elastic forces. They sometimes they are of interest when the constraint is that the surfaces differ by exactly 1. Then there were works on logarithmic variance of height functions of square eyes, and so forth. I mentioned before the work by Lammers and Ott on delocalization and the application of absolute value FKG to them. And then more recently, there's been a really new method formulated for the integer restricted Gaussian field by Pete Lammers, in which he produced an argument which, from my perspective, I would refer to it as percolation of boundary influence, kind of percolation analysis, by which he established existence of the delocalization of random height functions on any graph of cubic degree. So cubic graphs are graphs where vertices have always degree either 2 or 1, sort of 3, not more than 3. I would skip now the explanation of why this condition was important, but it played an essential role in his argument. Now, all that I am saying here is contained in this joint paper with which I mentioned before. Among the results presenting there is an extension of the statement proven by Lammers. So actually, let me now come to, oops, I spent all this time presenting the subject. Let me start talking about the new results. So the new results are these 3 points. First, we link the BKT phase, the phase of slow decay of correlations in a spin model that can be concluded that is linked directly with the depinning in the dual random height functions by a mechanism which I would like to explain. That leads to the conclusion that at any temperature for the spin system for which the dual height function depends, you have non-summable decay of correlations, which is another path to explain the existence of slow decay of correlations in the BKT phase. Since this gives relevance for us of the depinning transition, we also turned to the question of depinning and extended the validity of Lammers' argument to all graphs by essentially dropping the limitation on the graph degree. For that, we use the new correlation inequalities which I mentioned before. And what I find interesting particularly interesting and actually resonating with work of some people in the audience here, is that the link between the depinning and slow decay of correlations is actually placing the O2 spin model within the class of systems for which the spin correlations are actually looped with loop sub amplitudes. I will explain that. So for the rest of the discussion, I probably would be focused on the Villain spin model and it's in the ZGF, but the methods apply also to the XY spin model for which the dual field is referred to here as ZBF B for Bessel. So I should say that a contemporaneous approach to the BKT phase transition appeared essentially the same day as we uploaded the paper, the first version of the paper. That work is by Liss and Engel and Burke, and the reference is here. Okay, I have about 15 minutes to present the main new results, so let me turn to it. So in a way, what I would like to explain now is the meaning of this statement and why it's true and why is it relevant for us. So let's turn to the ZGF on the graph. So that's the integer valued height function. It's a function which is defined over the red dots, which are the, if you wish, faces of the in this case, the square lattice. The probability distribution, to remind you of the height function, is stated here, just proportional to e to the minus lambda, the elastic energy. Now, in such a situation, I would be drawing level lines, and since the function is defined over the plaquettes, we like to think of the level lines as passing between plaquettes, and the height of the level line would be taken to be half an integer. We say that the line passes through an edge if the value of the function is greater than q on one side and smaller than q on the other. So this is like a topographical map of random functions, where you should understand that as you go along the level line, the function is, the orientation is defined in such a way that the function drops on one side and rises on the other. So if you take the big picture, which is supposed to be conveyed by this, by this square, so that's how the finite system looks scaled down. So I do not draw here the lattice, which is minuscule on this scale. What you see here is what would be viewed under the microscope. So the big picture of this random height function is captured by level lines, which are oriented. And the main result which drives our analysis is that you show that the spin-spin correlation is actually bounded below by the probability that U and V, the two sides, happen to be on the same level line. Now that may ring familiar because this sort of expression in stochastic geometric terms of spin-spin correlation is something which we have encountered already in our discussions of quantum spin systems of certain type. So what I'm saying is that the Villain model joins this collection of systems. And what I would like to do now in a few minutes is to explain where is this coming from. So if you recall, the spin-spin correlation can be expressed as the expectation value of this disorder type operator. This T essentially is the operator which, let's see, you remember I talked about the operator T, which would be constructed by taking some a priori fixed choice of gamma linking the two sides, and taking expectation value of T means that we are looking at the ratio of the partition function in which we have introduced we encourage the system to produce a step across this line. The question is, how does this affect the partition function? This ratio is the spin-spin correlation. And the bound which we are presenting here is fed by the simple inequality that whatever is the value of this, you get a lower bound by looking at a certain type of configurations, and the type of configurations is defined by the condition that there is a level line linking. Oh, sorry, I switched here X and Y. Linking the two sides, we have X here and Y there. The event A, the chi is the characteristic function, AQ, this is a mouthful of a symbol, but in plain language, we set an exploration path from X to Y to check whether the two sides per chance are on the same level line. And I have to explain how does this exploration work. The definition is stated here, but let me first do it in terms of this picture. To determine whether X and Y are linked at the same by a Q level, remember Q is half an integer. To be linked by a Q level, it means that along there is such a path along which the function is higher than Q on the left side and lower than Q on the right side. The trick here is to come up with an exploration process which does not generate more information than needed. Basically, we want to return the Markov property of the model and have a conditioning which whose effect can be kept track. So the algorithm is described, I think, on the next page. But basically, you choose an orientation to start. You check, is the function higher than Q to the left and lower than Q to the right? If so, you proceed. If not, you stop. Next step, you explore first the right turns, if possible, and if not, you start looking to the right, whether you can turn. If you could not, look at the next direction and so forth. And you accumulate information about the values of the of the random function along such a path. If you pay attention to the detail, you would see that the information that you accumulated tells you something about the values of the function along a set which is connected on the right and only star connected on the left, but these are small details. Now, in such an exploration process, you may actually realize during the exploration that actually there is no way that this and this are connected. In fact, there is no path at Q which starts it from here, or there is a path which starts and closes on itself or hits this set gamma. If that happens, you just do nothing. You notice that the event A did not occur. However, A, Q tilde gamma XY, this complicated symbol, is the event that the exploration process actually produced a path which, starting from here, hits Y without previously hitting the path which we selected as gamma. And now the point is that when you condition on this event, the effect of T is actually bounded below by 1. So the expectation value of this disorder operator is bounded below by its expectation times the indicator function that the exploration actually succeeded. And then the T result, which physically corresponds to positivity of the stiffness modulus of this random function, of this random height function, the stiffness modulus is positive. So let me try to explain that. The quantity which we are after is the expectation value of this disorder operator times the indicator function. The claim is that, first of all, this can be viewed conditioned on the information. So conditioned on the information which is gathered by the exploration process, this can be presented as the ratio of partition functions. Let me go back to the picture. This is the partition. I'm conditioning on what we learned through the exploration process, limiting myself to the case that the exploration succeeded. And based on this, you accumulated some information which says that the height function is systematically here on the left side greater than Q, on the right side smaller than Q. And the bottom line is that when you condition on that, due to the careful selection of the process in which no further information is generated, by the Markov property of the measure, the conditional distribution of the height function elsewhere is just the Gaussian state with this as boundary conditions. Now notice that the boundary conditions actually are such that we stress the system, we condition on there being a step up in this direction, and in that case, what we prove is that the effect of this disorder, this operator T, is actually positive. It's the expectation value of T conditioned on this event is greater than 1. Intuitively, if you have an elastic surface which you stressed in this manner, there is no penalty for actually discounting, for encouraging the random height function to have a step along this line. To the contrary, the expectation of this is greater than 1. So time is running up. I will just state the basic, we refer to this as the positivity of the stiffness modulus. The intuitive picture is that if you introduce a strain, that would actually welcome the other term T. That would the ratio of these partition functions is going to be greater than 1. Since time is running fast, I would not dwell on this. I hope that what I said intuitively conveys the picture. But just to get, there are many moving parts in this argument, so to get to some others, let me just quickly list those. So the positivity of the stiffness modulus implies that the spin-spin correlation is bounded below Well, there is a factor of 1 minus epsilon for technical reason. It has to do with the question of how do you select Q in this exploration process. Let me skip it. Feel free to ignore that. This is just a repetition of the inequality which I stated before. Now, there is a loop-sup argument which occurs in many other situations. So let me just quickly describe it. There are various other situations that actually I see people in the audience who wrote about such things. There are situations where you have a Gibbs measure described, where you have a distribution of what's referred to as loop-sups. These are ensembles of loops which do not cross. They may be dense or not. And in some cases, like I mentioned, some quantum spin systems, the spin-spin correlation is bounded. Sigma x, sigma y is greater or equal than the probability that x and y are connected by a random level line. Let me call it, in our case, it's n. For spin models that we encountered before, you have an equality. Here you have an inequality. That's somewhat unusual. But in that situation, notice the following, that when you have a system of random loops, then one of the two, a relevant question is to ask whether the number of loops encircling actually, sorry, let me refresh the drawing, sorry. With a natural question when you have a system of random loops is to ask whether the system admits an infinite family of loops encircling the origin. If there is such an infinite family of loops encircling the origin, you would have an infinite family of loops encircling any other point. If so, one of the two, you either have an infinite nested family of loops, in which case the height function delocalizes because the variance of the difference between the height at 2 points which are separated by a large number of loops, the variance is proportional to, is greater or equal to the number of such loops. So delocalization is going hand in hand with the existence of infinite families of nested loops. And in that situation, notice that the sum of this, if you the sum of the 2-point functions sigma x, sigma y, where x would be summed over. Let me sum x and y. X over, I'm not writing it here, but x would be summed over the horizontal axis, y over the vertical axis, as indicated here. That would be greater or equal than the number of loops encircling the origin, because each loop contributes at least a single pair for which this is satisfied. And from this, you see that if the expected number diverges, the sum of the 2-point function diverges. And if you use translation invariance, which we do have in our model, that is actually nothing else than just the susceptibility, the regular susceptibility, in the sense that by translation invariance, that is equal to summation of the correlation between 0, 0 and correlation between x and y. So it's just a regular sum of the 2-point function. So by this canonical argument, if you have such a relation, then the divergence of the number of loops encircling the origin implies that the 2-point function is not summable. So Then there is another, oops, I somehow lost another, so that's this observation. By this loop-soup argument, you can conclude that the pinning in the random height function implies divergence of the sum of the 2-point function, where you go from 0 to an arbitrary point. Then, from this, you can actually, this statement can be bootstrapped through the 2-point function dichotomy. Let's see, do I have a minute to finish the argument?
Yes.
Yeah. So, thank you. So, it's a general principle which applies to many systems. It goes back to the Dobrushin and Pechersky theorem about general statmech problems, and later was simplified for spin models in the Simon and then deep Simon inequalities. Systems which obey those inequalities have the property that you have a dichotomy. The 2-point function is either exponentially decaying, positive mass in the language which was mentioned earlier, or else it does not decay faster than the inverse length. This is actually a consequence of the Simon-Lee type inequality. This inequality was derived in 2 different forms for the XY models in the special issue of CMP, which seems to have a string of short papers expressing this fact in various contexts. The Villain model was not listed in this production, but actually the Villain model obeys this inequality. The fact that it does is really cool, and I just cannot resist the temptation to say that. So let me say remark. If there will be a question, I would explain what is the Simon-Lee inequality, but for those who know, let me just quickly make the following remark. There is a nice way of thinking. The Villain model can be thought of as describing a spin function where the spin is sigma x is e to the I theta x. To understand what's really Villain model, you may notice that you may extend the definition of the spins, which originally were associated with the vertices. You may extend the definition to the metric graph, which is obtained by thinking of functions supported on the edges. Actually, if the action of the Villain model corresponds precisely to what you obtain if you think of a continuum, kind of one-dimensional continuum version of these unitary spins, which condition on the values at the edges perform just Brownian motion on a circle as you go from one end to another. This very neatly explains this particular form of the action of the spin model. And in fact, more is true. The Villain model can be thought of as collection of Brownian motions on circles along the edges, which are constrained to be consistent, to give a consistent spin picture, consistent in the sense that there are different ways to get from one side back to itself, and you want all of those to perhaps differ by the number of winding numbers, but produce the same spin value. That is the Villain model. Now, and then you may realize that this Brownian motion is so natural that actually it can be presented as the continuum limit of the XY model. So here is a what I find cool statement. So let me clean this up. There's a way to, okay, what you can do is think of this continuum model, which I just mentioned, as the limit of systems where you chop the segments into small intervals, and you consider XY models on the sides of this enhanced graph with couplings which are driven to infinity, so that the probability of a so that the variance of the spin actually, the variance over short segments is very small. So the countings are driven to infinity, but at a rate which produces a mass gap in the term which was used before along a single edge. So V-lane is the limit of XY models. And using this relation, the Simon-Lieb inequality, which was proven for XY model by Lieb and Rivasseau in that special issue, in that issue of CMP, actually allows you to conclude that the V-lane model also satisfies this. And that inequality produces the dichotomy. The advantage of the dichotomy is that once you have proven that you have, under the pinning, you have such a slow decay of correlations, you can immediately conclude that actually the stronger statement, that the correlations decay not faster than 1 over the distance times a constant. I just recently mentioned this in a talk and learned from Sebastian Ott that our friend Chuck Newman actually made a similar observation about the V-lane model being limit of XY systems fairly recently. And this being Chuck, of course, for him, this was of particular interest because this was used by him to prove that the V-lane model also has the Lie-Yang property, something that Chuck Newman has been working a lot on. So so putting these 3 elements together. So first is the positivity of this tensile modulus of the random field. Then the loop sup argument, which implies that the pinning implies the divergence of the number of loops encircling the origin, the mean of that implies non-exponential decay. Boosted by the dichotomy, you get a lower bound of this form. Now, the only thing which is left is to describe a simple proof of the pinning on various graphs. I would skip that here. So actually, this is the last, I think that this is the last transparency which I wanted to show. Part 1 is just what I explained. Part 2, the delocalization, we do not have time for that, but the details are in the paper, which is on the archive. And I mentioned other spin systems for which this relation between being on the same level and spin-spin correlation plays a role. One of those is our joint work with Bruno Nachterhalle on geometric aspects of quantum spin states. There are various other works on this theme. Some are presented in this work of Daniel Ulci. There are more in joint work of Daniel Ulci and Bruno Nachterhalle and other people. More recently, such a relation was actually used to show that a loop ensemble, the loop sup ensemble of loops, actually it's one of those very natural mathematical scaffoldings which play a role as scaffoldings for a variety of very different looking spin models. And some of that was presented in the joint work of 2020 with Hugo Dominiel-Copin and Simone Varzo. And finally, let me say that the contemporaneous approach to, alternative approach to the Bogolyubov-Kosterlitz-Thouless transition, which does not use the pinning but produces still another proof pretty much in line, resonating with what we discussed, derived independently, was presented by Liss and Engeldenberg. Which brings me to the end of my talk. Thank you for your attention.
Thank you very much, Michael, for the beautiful presentation. So now we ask for questions and comments. Any questions or comments from the audience?
So perhaps one question, if I may.
Yeah.
Yes, please.
So you did not describe too much in details the results on delocalization. I mean, when you generalize the work of Lammers. My question is whether, I mean, Lammers has this this restriction, but the nearest neighbor interactions needs to be less than, is it log 3 or something like that?
Yeah.
Would it be possible to handle a graph where some couplings would be stronger and some couplings weaker.
Not by the original argument, but I think that you may hope perhaps to renormalize that argument. Basically, what Lammers does is sort of a percolation of influence argument. Basically, just to explain what it is, you take a large system and you have a certain graph. And the question is, does the system delocalize or not? And just to summarize the argument, you may look at the percolation of the level sets where nx is greater or equal than 0. If this set does not percolate, so you look at the set of x when n of x is greater or equal than 0. If this set does not percolate, it means that a site would be encircled by a loop along which n is less than 0. And then by the Markov property, it would imply that the Gibbs state with 0 boundary condition actually is the same as the Gibbs state with lower boundary conditions. Now, and that implies delocalization by simple mental gymnastics. So what you want to show is that this set does not percolate. And what Lammers does is the following. You know that you cannot have simultaneous percolation of set when n is strictly greater and strictly smaller than 0, because two such sets cannot pass. What Lammers does is actually switch by adding a clever designation of edges. He maps this percolation influence onto percolation along edges in a system where at low enough values of lambda, the edges are marked either plus or minus. I mean, there's a technical point there. And now, for a cubic graph, you just cannot have simultaneous, you cannot have paths which cross, which are both, you cannot have both plus and minus path crossing if the plus or minus refers to coloring of edges. Unlike, for example, square lattice, in which plus can cross minus. Cubic lattice, you cannot do that. So to answer your question, the original argument does not allow you some small exception, because the whole thing is to really rule out the small exception when n is equal to 0. In principle, never say never. You may think of some sort of renormalization of this by some finite volume condition. So I do not think this through. There may be room for improvement. In fact, to highlight the limitation of what we did, and there is room for improvement, a nice feature of the Coulomb gas analysis of the Bogoliub of the Kosterlitz-Thouless transition is that it admits some sort of renormalization argument, which allows you to learn further details about the actual rate of decay. It would be nice to develop some sort of renormalization version of what I described. And I have the impression that some people are thinking about that.
Thanks a lot.
Any other questions? Okay, let me ask one question. So this relation between X, Y, and Bilal model is very interesting. Is there anything corresponding? Is there any corresponding relation for the dual height systems?
Oh, yeah, that's a good point. Yes. The Villain model, as I said, in a way, when you think of it in terms of Brownian motion along the edges, this is so natural that it's a nice starting point. And then, but then you may ask, how does XY fit into that picture? It turns out that on one hand, the Villain model can be viewed as the continuum limit of XY, continuum along a single edge. And then the XY model can be viewed as a annealed average of villain type couplings. Namely, there's you can think of the dual to XY, which has an action which is described by the Bessel function. I mean, the Gibbs factor is a Bessel function of the coupling constant. You may think of this Bessel Gaussian, Bessel field, as an annealed version of villain type of simple, sorry, annealed version of the integer valued free fields, where you integrate over possible couplings, but in an annealed manner, rather than a priori fixing them at random. You select them at random, but it's an annealed process where the actual weight incorporates the effect of this randomness on the partition function. So they are arrows which go back and forth between these two models. And the results which we presented actually extend to the more general class of height functions with annealed Gaussian interaction.
Okay, yeah, that's also what I wanted to ask. So you only talked about XY and villain, but
Yes.
they are the only two examples of a bigger class that you can treat.
Yes.
Is that correct?
So the general class is that we can handle, and which is handled in the paper, are systems whose interactions can be viewed as annealed Gaussian.
Okay. Any other questions? Is that okay? I have one more question. So you have shown this lower bound of sigma spin correlation in terms of this probability that two sites belong to the same height, same level loop, something. But it's of course more natural. So in random walk representation, this U and V are now connected twice by two random walks. So is it of course true? Is it correct to think that this lower bound is not at all optimum, or this upper bound and lower bound have different decay power of decay or something like that?
Yeah, I think that it's not optimized yet. Yes. Yes. I do not think that it's. It may not be given let's see. There may be something lost indeed in this inequality. Somehow the entropy may not be fully taken into account.
So this is almost a stupid question, but it is known that this critical value of eta parallel decay is 1/4 for the XY model. Is there any hope of understanding this 1/4 by using this kind of stochastic geometric arguments? That would be nice.
I tend to be optimistic usually, but I do not want to indicate that I really know how to do it. At this point, I don't. But it's a very natural question, and it would be nice to learn how to.
Some super version of Simon Leap and things like that. Yeah, thank you.
Yeah, you want to understand a bit better the normalization perspective on that. And it so happens that there was just a meeting where I, for the first time, ran into Pete Lammers, and I have the impression that there may be some room for improvement here. And some people are thinking about that.
Thank you. Any other questions? Okay, so if not, let's thank Michael again for the wonderful presentation. Thank you.
Thank you.